time to time. Wave theory of light, Planck's quantum theory. So after few theories, then came Huygens principle. So in order to know what is this principle, we have to understand the term that is known as wavefront. Now see, just in order to understand, take an example. An example to understand what is a wavefront. Suppose a stone is thrown on a surface of still water. If a stone is thrown on a surface of still water, then won't you be able to observe circular patterns of alternate crests and troughs? The ripples in the water will be generated if you throw a stone in still water. So see what will happen. All the particles lying on crest are in position of their maximum upward displacement. Similarly, all the particles lying on the trough, means on the downward portion, are in the position of their maximum downward displacement. So all these are in same phase. So what happens? The locus of all the points oscillating in the same phase. This is what is known as a wavefront. So a wavefront, it is defined as a continuous locus of all the particles of the medium which are vibrating in the phase at any instant. So a wavefront is a surface of constant phase, means the phase does not change, phase remains same. And the speed with which the wavefront moves outwards from the source, this is known as the phase speed. This is known as the phase speed. So wavefront is what? Wavefront is continuous locus of all such particles. Just now in terms of wave theory, this was just an example. In terms of wave theory, the stone that you have dropped in the still water, this stone will act as a source of light now. Now just compare it to the wave theory. So if a source of light is there, all the particles of the medium that are in the same phase, which are vibrating in the same phase, forms wavefront. Understood what is meant by wavefront?
Yes, teacher.
Okay. Now see, there are various types of wavefronts depending on the shape. So firstly, we have a spherical wavefront. See, in case of waves traveling in all directions from a point source, I hope you understand what is meant by a point source of light or any point source. So in case of waves traveling in all directions from a point source, the wavefronts are spherical in shape, like in concentric spheres. This is the case for what? For point source. So in case of point source, all the particles are forming spherical shape. Now the reason is that this is because all such points are equidistant. If this is the source of light, then all these points are equidistant from the point of source which lie on the sphere. And the disturbance starting from the source will reach all these points simultaneously. That's why we get spherical wavefront. Now see, remember one thing, that the rays of light are always perpendicular to the wave. So if I represent the ray of light, if these are the spherical waves, then one of the perpendicular will be in this way. So this is a ray. Ray is nothing. Ray is an arrow drawn perpendicular to the wavefront in the direction of propagation of ray. This is known as ray. It's just an arrow and it's a representation. So see, in case of spherical wavefront, one of the ray will be like this. Other ray that will be parallel will be in this way. So similarly, all the rays will be parallel. Sorry, not parallel, perpendicular to the surface, means making an angle of 90 degrees. So a ray, an arrow drawn perpendicular to the wavefront. See, these are the spherical wavefronts. These are the spherical wavefronts. So an arrow drawn perpendicular to the wavefront in the direction of propagation of wave. This is known as ray. So in order to understand, you should remember that this ray of light, represents the path along which light travels. So for spherical wavefront, all the rays will be light because these will be perpendicular. So this was the case of spherical wavefront. So first type of wavefront we'll get is spherical, that is valid for a point source. Now see, second wavefront that we'll be getting is a cylindrical wavefront. Now see, when the source of light is linear in shape, when the source of light is linear in shape, so linear shaped source of light. For a linear shaped source of light, such as fine rectangular slit, the wavefront is spherical in shape. So wavefront will be like this. Normal symmetrical cylinder that you know. Now see regarding the ray. And understand, this is because the locus of all such points are equidistant from the linear source of light, that will be the cylinder. So over here, the source of light will be linear, like this. Previously, in case of spherical cylinder, the source of light was point source. That's why all the wavefronts that we were getting were spherical. When we have linear shaped source of light, then because of this linear shape, the standing line, all the wavefronts that will be drawn all along will be cylindrical shape. So if you draw the rays will be like this, perpendicular to this. This is the source of light. And what I have told you, rays are perpendicular to wavefront. If this is the wavefront, so perpendicular to it will be this. So this will be the direction of the rays. One more type of wavefront we have, that is the plane wavefront. Now see, as a spherical or cylindrical wavefront advances, its curvature decreases. This means if I have a circle, all right. Now if I cut a tiny portion of the circle, I'll be getting a curve, right? Yes or no?
Yes,
Yes,
teacher.
ma'am.
Okay. Now if I increase the radius and the diameter of the circle, I take a very huge circle. And then if I'll be taking that small tiny portion of it, I'll be getting a straight line. Will I be able to get this line or not? The straight line or not?
Yes, ma'am.
So what happens? As a spherical or the cylindrical wavefront advances, means the diameter increases, the radius increases, the dimensions increases. So its curvature decreases. This curve decreases. The smaller is the circle, the more is the curve you get for the tiniest portion. So as the curvature decreases progressively, a small portion of wavefront at a large distance from the source will be a plane wavefront. So a plane wavefront is for the larger curvature of the spherical or cylindrical wave. So it can be represented like this. These are the plane wavefronts. Now see, how do we draw the rays? Parallel to the wavefront or perpendicular to the wavefront?
Perpendicular.
Perpendicular. So perpendicular to the wavefront, these kind of rays will be passing. These rays will be perpendicular. So these represent the rays, and this is the plane wave. All these are the plane wave. So for a plane wavefront, as the curvature decreases, we'll get plane wave. Now see, now your concept comes of ray optics, diverging and converging. Now the two types of wavefronts that are left are diverging wavefronts and converging wavefronts. Now see what is meant by a diverging wavefront. If I'll be getting various curves, various wavefronts, and not complete sphere, just a part of the spherical wave. I have all these. Now see, if I draw rays, and rays are always perpendicular. So perpendicular to this, if this is the source of light, let's say, perpendicular to this will be like this, then perpendicular will be this, and another ray that is perpendicular will be this. So now see, these red lines represent the ray of light, means the path along which the light travels, and these are the diverging wavefront. So basically it's a part of the spherical wavefront only. If I complete the spheres, then I'll be getting spherical wave. So these are the diverging spherical wavefronts, you can say, or diverging wavefronts. So it's not a different type of wavefront, it's actually a part of spherical wavefront only. And if I take the opposite side, means if I, instead of this part of the circle, if I take the opposite part, like these parts. Now see, when I'll be drawing the rays that are perpendicular to the surface, so what will happen? These will be perpendicular to the surface for the source of light. So what is happening? These rays are appearing to converge. So these are the rays of light, and this is the yellow line have been representing the converging spherical wave. Understood or not?
Yes, teacher.
Yes, ma'am.
All right, so just note down these and we'll begin with science. And wherever you have to ask me, just ask.
So can you scroll up for a minute? Okay, teacher.
See, Noor, the source for converging wavefronts is in the center only. Like, see, this is the sphere, this is the center of the source, this is the source placed in the center. Now, see, if I just take this part, if I cut this part, will I be able to get the diverging? And if I cut this part, I'll be able to get the converging. So that's why there are mainly three types of wavefront: spherical, cylindrical, and plane. Just a case of spherical wavefront are the two, converging and diverging. If I cut this portion and look at this, so see, this will act as a diverging source of wavefront.
Ma'am,
Yes.
I can't see anything from the screen. I mean, it's still on spherical wavefront.
What?
I can't see what you're writing.
No, I'm not writing anything. See, is this screen sharing with you all?
Yes, teacher.
Yes, teacher.
Okay, see, no. First, understand what is spherical wavefront. Have you understood what is meant by spherical wavefront?
Yes, ma'am.
Okay. Now, see, if I cut this part, means if I draw a line and separate the spherical, will I get this part from all the spheres I have? If I cut this part, I'll be able to get this only? Yes, no.
Yes, ma'am.
So where is the source of light for this? The source of light for this is the source of light for this only. So the source of light is kept in the center only. That is the point source of light. Now see, the source of light will be here only. Just imagine, if you complete them, you will be getting complete spheres. That is what we have discussed for spherical wave. So see, the source of light remains only at the center and the surrounding are the spherical wavefront. If you take a portion from the right hand side, then you will be getting diverging wavefront. See, those rays will be in this form. So the source of light will still remain in the center. And if you take it for the left hand side portion, for these, then also the source of light will remain in the center of the sphere. So understood? Where is the source of light?
Yes, ma'am. I understood.
So should I scroll it down or anyone is writing this?
You can scroll down.
So these are the rays. And this yellow line is the cylindrical wave. This is the wave. Written?
Yes, ma'am.
All right. Now let's see Huygens principle. See what it is. Each point on a wavefront acts as a fresh source of new disturbance called secondary waves or wavelets. Secondary wavelets spread out in directions of speed given. See, understand what is meant by this. Huygens principle, basically the statement is that each point on the wavefront that we have discussed previously. So each point on the wavefront is a source of secondary wave, which finally add to give the wavefront at any later period of time. Now see, let us, in order to understand this, let us take a spherical or a plane wavefront. Let us take a spherical wavefront. So the source of light or the source must be somewhere over here, and we are getting a spherical wavefront. Let's name it A, B. This is the wavefront. Now see, AB be its position at any instant of time. Now see, this region on its left has received a wave. Let's say this region has received a wave, while this region on the right side is undisturbed. Now, according to Huygens principle, what this is trying to imply is that each point now on AB, this wavefront, this becomes a source of secondary disturbance. So each point is now acting as a source. See, this was the primary first source that was generating a wavefront. Now what is happening? Because of some waves, because of some disturbance, because of the reception of some waves, each point, all the points I'm not marking, but all the points are now acting as source of light. They are again now acting as source. So what will happen? These are source of secondary disturbance. The primary disturbance was created by this. Now each point on this AB spherical wavefront is acting as source of secondary disturbance, which travels with the same speed of light. What is the speed of light?
3 into 10 is 5.
3 into 10 to the power 8. Now see, if this is acting as a source of light, what will happen? It will create a wavefront of its own. If this point is acting as a source, then this point will also be creating a spherical wavefront. So what will happen? These wavelets will be created. So to find a new wavefront after some time, we have drawn the spheres from each point on A. So these kind of secondary waves will be generated for all the points that is present on AB. So now see, we are getting a forward envelope or the tangential surface. Now see, as I've told you, rays are perpendicular to wavefront. So perpendicular to the wavefront, after this what we'll draw? The final, if we join all the rays, it will form another spherical wavefront. Let's name it as CD. So AB was the primary wavefront. Now it has generated another wavefront, that is CD. So all these lines, all these spherical radius of the wavelets, these are perpendicular. As I've told you, ray of lights are always perpendicular to the wavelength. Now see, if we draw the tangent on all this space, we'll be getting CD. Now see what will happen. Again, point of light, this will act as a new disturbance. So all the points on CD will be now creating secondary waves or wavelets. Then again, similarly, these wavelengths will be created. These wavefronts can be created. Understood? So see, I am repeating. We have considered a spherical wavefront AB. All right. Or you can take it as a plane also. You can take the example of a plane wavefront also. If anyone wants, I can repeat it for plane wavefront as well. Now see, this is moving. This is a plane wavefront. So the region on its left has received a disturbance. It has received a wave, but the region on its right hasn't received any wave, any disturbance. So this region on the right is undisturbed. Now, according to Huygens principle, each point on AB becomes a source of secondary disturbance, which travels with the same speed of light, that is c, 3 into 10 to the power 8 meter per second. Now, to find the new wavefront after time t, we draw the spheres of the radius ct, mean speed of light multiplied by t time. So the forward envelope or the tangential surface of the secondary wavelets, these red lines have represented the secondary wavelets. So all the forward envelope or the tangential surface CD of the secondary wavelets gives the new wavefront after some time, let's say t. So this is what was written. Each point on a wavefront acts as a fresh source of new disturbance. All these points are representing the new waves. So the secondary waves spread out in all the directions, and with what speed? With the speed of light that is given in medium, that is c, 3 into 10 to the power 8, which you all are aware of. And the new wavefront at any later time, it is given by the forward envelope. What is meant by this forward envelope? This tangential surface in the forward direction of the secondary wavelets created at that time. I hope you know the tangent on the surface. This is how we draw a tangent. And if there are various spheres, and if you connect all the tangents, then it will form a curve. Is it clear or not?
This one is clear.
Yes, teacher.
No. Just note down this. Similar will be for a similar will be for a plane wavefront. Okay, one more thing. I can also draw a wavefront in over this side also. Why I have only drawn the wavefront CD on the right hand side? If the question was, or if the point was to draw envelopes that are tangential, then these points are also tangential. Then I could have drawn these also. Any idea?
It's given only by the forward envelope.
Why? Why? Exactly. Why only the forward envelope? Why not the backward?
Because the rays are traveling from the source.
Yes. See, no backward wavefront is possible. And the reason is that there cannot be backward flow of energy during the propagation of a wave. That's why I have not considered these. Otherwise, I could have drawn them. But energy cannot propagate backwardly. That's why. Just text me in the chat box and you all have Okay, Amelia. See, I was saying I cannot draw a backward wavefront like this. I have drawn CD in the forward portion. All these tangents have been connected in the forward direction. I could have connected them backward. A backward envelope could also have been. But why we have not taken this case? Why I haven't connected all these from the backward side? See, the reason is that there cannot be backward flow of energy during the propagation of a wave. So, because energy cannot be propagated backwardly, that's why backward envelopes have not been considered. Is it clear, Amalia?
Yes, teacher.
So, you all have written, or anyone is writing?
No, teacher.
This one is
Okay, so this is a question. It says that discuss the behavior of plane wavefront when it passes through prism, convex lens, convex mirror, concave mirror. See, all these terms you have covered in ray optics. Now let us connect it to the wave theory. First one is prism. So we have to discuss the behavior of a plane wavefront when it will pass through a prism. So for a prism, let me draw. So see, this is the incident wavefront. Because question has already demanded for plane wavefront, that's why we are not considering different spherical wavefronts or cylindrical wavefronts. So this is a plane incident wave, and this is the prism. Now see, in order to understand behavior of prism, you have already covered all the properties of prism. You have seen in the class. I hope sir has completed prism.
yes, ma'am.
Yes, teacher.
Okay. Now see, since the speed of light, okay, anybody has idea whether the speed of light is greater in glass or it is greater in air?
It's greater in air.
Then air.
Greater in air. So see, since the speed of light in glass is smaller than in air, lower part of it, let us name it as A, B, C. A, B, C is the incident wave. So the lower part, C, of the plane wavefront, this travels through the greatest part of the prism, this thicker, broader base. So what happens? This speed is slowed down most of the time. While the upper part of the incident wavefront, this point A, this travels through minimum thickness. This is the minimum thickness of the glass prism. So this is slowed down the least, means the speed is maximum. So what happens? Since it will be, the speed will be more in case of A part because the thickness is minimum over here. So if the thickness is minimum over here, then what will happen? The speed of light, that is the speed of the wavefront, will be more. So if I draw a spherical wavefront or just the markings for the wavefront, so if this is the point source, then I'll be getting a bigger sphere. So I won't be drawing the whole circle. I'll just take a part of it. Let's say it'll travel to a bigger distance. This is just a marking for the point A. Now let us take it for the point C as well. So what will happen? For case of point C, this has to travel through a greater thickness for the base of the prism. Now see, if I draw a marking for it, it will be like this, nearer to it. Now if I connect them, the way we have seen it for the previous case, how we all connect the tangents of it. So see, if I connect the tangents, I'll be getting a ray of light like this. So if I connect them, this will be till here. It will be a straight pattern. and then it will climb. Similarly, it will be for C. This will be the ray of light till the prism. It will deviate and reach over here. So this was the incident wavefront, and let's say A dash, and this is for C, so it would be C dash, and what middle part is B, so it will be B dash. So this ray of light that I am getting on connecting the tangents of the spheres, this is my refracted wave. Because what phenomena has occurred, or which phenomena occurs in prism? Refraction only. Refraction of light occurs. So in case of wavefront also, the ray of light that is received at the other end, this is a refracted wavefront. Understood behavior of prism?
Yes, teacher.
Now
Can
see
you
second,
explain that A dash part?
sorry, this part,
Yes, teacher, like the curves. Which you do.
these curves.
Yes, teacher.
Okay, see, actually these are those curves only. If this is a point source of light, how do we draw the curve? This is the curve for the source of light. This is how we draw a sphere basically around the point source of light. Now see,
Yes,
in
teacher.
case of this, if this is a source of light, a very broader and a very larger sphere will be drawn, which is not possible to draw in for every question that you will be getting or for every part. So in order to concise it and make the derivations also and the questions precise and to understand it better, we usually write just the curve. So actually it's a part of the sphere only, of the spherical wavefront only. If this is the source of light, then we have a sphere only. So we have just taken a sphere, part of the sphere. So actually if A is acting as a source of light, all these things are closer to each other. For us to understand, I have drawn it through a larger separation. So this cut, this sphere I have drawn, this curved part, this is actually the curved wavefront for this point A only. The dotted lines are the secondary wavelets according to Huygens principle. Yes, Noor, the dotted wavelets represent the secondary wavelets, like this. See, if this was the source of light on point on this spherical wavefront AB, this point was a source of light. Then what happened? We have got secondary waves or wavelets. Now, if I just draw this part only, so this will appear in the form of a curve only. So these curves I have represented. So throughout the calculations for interference, for diffraction, for all the phenomena, you will be just writing the curve, because drawing the whole sphere is not possible every time. And there's no need of the lower part also, because you do not connect them. So you just need the forward envelope only and the upper part of the sphere circle only. So these spheres are these only. And the way I have connected them, I have connected these also, like this.
Teacher,
Is it clear now?
teacher,
Yes, Abdullah.
teacher, the first curve, right? Like it's little far from the prism, while the second is little near the prism.
Sorry, can you
The
repeat?
first curve is like the first wave, the first secondary wavefront. A
The
dash.
first, yes, A dash is.
A dash. It's little far from the prism. While
Yes,
the
this is far. That's why I was telling you. See. That is because of the speed. See, this is glass. Prism is made up of glass. And this part is air. So what happens? Since the speed of light in glass is smaller, the speed gets reduced. So that's why the speed is more over this part, because the glass portion is very less. This is the minimum thickness part. Since the speed of light in glass is smaller than in the air, this lower part C of the plane wavefront, this travels through a greater thickness. This is receiving much part of the glass. So this lowers the speed. This reduces the speed of all the wavefronts that has been generated from this point. So that's why we get a wavefront over here only. Whereas in case of A point, actually this should have been drawn like this. This is like this only. If this is the prism, this is the wavefront. Both are neck to neck parallel. Now see, for case of A, for the upper part A, this travels through minimum thickness of the glass prism. So this, the speed that is slowed down, this is the least, means the speed is maximum because more part of the rays have been covered in air only and speed is more in air. So that's why they travel through a greater distance. That's why this explains the tilting of the refracted wavefront. Understood? That's why tilting of plane wavefront occurs after refraction through glass prism.
Yes, teacher.
Okay.
Yes, teacher.
Okay, so let us see for all the other devices also. Convex lens. Let's see it for convex lens. So a convex lens is a converging lens or a diverging lens?
Converging.
Converging.
Converging. Now see, regarding the wavefront, the type of wavefront, the question has clearly mentioned that we have to use a plane wavefront only. So this is a convex lens. That's how we represent a convex lens. Now let us take the plane wavefront. This is the plane wavefront. Let's also name it A, B, C again. Now see, the similar phenomena will occur. This part is the thickest part. So what will happen? The rays that will be coming from this part, this will be nearer to it, like this. All the space that will be coming nearer to it. Because this is a broader space and the light rays that will be coming from the middle part, that is for the middle portion B. What will happen? The rays have to travel a much thicker distance. So this reduces the speed and the wavefront is formed over here. Whereas for the case of A and B, both are at the same level and both have to travel the same amount of minimum thickness for the edges of a convex lens. So what will happen? A wavefront, let's say, over this distance is formed for part A. And similarly for part C, if this is acting as a source, somewhat this kind of, no, I have drawn it inverted. Since it's a part of it, it will be facing it only. So let's say this is for C. Now see, regarding the wavefront. Now how do we make the wavefront, the final wavefront? We ultimately join the rays tangential lines. So what will happen if I join all the tangential lines? I'll be getting a curve. So this, I'll draw it again because the lines are not matched. So for B, it would have been over here. For A, it would have been over here. And for C, it would have been over here. So this kind of wavefront angle. So if I wish to represent the direction of the lines, what will happen? From A, it will be till here. Then since the lens is a converging lens, it will converge. Similarly for B. And similarly, it would be for C. So rays will converge. And why are the rays converging over here? Is because of the property of convex lens. Convex lens has the tendency to converge rays. But what is new thing over here is that the direction and the representation of the refracted wave. So this is the refracted wavefront. And this ABC was the incident. Now see, similar to it. Now for concave lens, see, nothing will be different. It's just that what is the property of concave lens? To diverge rays or to converge rays?
Diverge rays.
Diverge. Now see, in case of concave lens, let's say this is a concave lens. This is the incident wave. Now see, the final refracted wavefront that I'll be getting will be just opposite to that of the convex lens. See how? For this part, let's say A, B, C again. If I draw a wavefront, that is secondary wavefront according to Huygens principle for this A part, somewhat this kind of curve I'll get. For B, now the things have been reversed. How the questions have been reversed and the properties, the edges are now broader and the middle part is thinner. So the light has to cover more of air and less of glass for the middle part. That's why it will go further. And for C portion, this will be similar to A. Let's say I have drawn it reversely because it becomes difficult to connect all them. That's why. Otherwise, first you need to draw these and then you connect all those. And if I draw it for the rays, so what will happen? From the A, it will reach over here. And since it is a diverging ray, diverging lens, it will diverge all the rays. So similar would be for the C part, and it will diverge. So these are the rays and these are the diverging rays. So what is this? What is this curve representing?
Refractive wavefront.
Exactly, refracted wave. This is the refracted wavefront. So this property is because of a concave lens. So main thing that you have to understand is that only variation because of speed only. See, wherever there is less of glass, more is the speed. Wherever there is more of glass, less is the speed. And that is the reason only because of that speed of light in case of glass is greater than the speed of light in glass. Speed of light in air is greater than speed of light in glass. Now see, these were regarding the lens. If we have it for the mirror, let's see it for the mirrors. If we have a convex mirror. So is a convex mirror diverging mirror or converging mirror? Yes, convex mirror, diverging. See, it's opposite to the lens. In case of lens, the convex lens is the converging lens, but the convex mirror is a diverging mirror. So see, if you have a convex mirror, actually your reflection portion was deleted from your syllabus, na?
Yes, teacher.
Yes,
So
teacher.
you have done only refraction. Okay. So see, convex mirrors are the diverging mirrors and the concave mirrors are the converging mirrors. So see, convex mirror is a part of a sphere which is silvered on its inner side, like this. This is a part of a sphere and this is polished or silvered on its inner side. This is the reflecting surface for a convex mirror. So see, if I take a plane wavefront, this, let's name it A, B, C. Now what will happen? When light rays will fall on this, light rays will be falling on it. So since a convex mirror is a diverging mirror, it will diverge. Similarly, from the lower part also, it will reach and this will get diverged. Now see, regarding, this is the plane, this is for the case of light. Now see, let us relate it to the wave theory. This is the case of reflection that has been deleted. So that's why you all are not aware. Otherwise, this is the general case for a convex mirror. Now regarding the wave theory, how we have to get the wavefront. See, for this point, see, this is the curve is over less curve is there. If this is a source of light, this point will acting as a source of light. So this is a less curved part than the broader part that is in the middle. So what will happen? I'll be getting this kind of curve. This is a bulged out part. So it will travel a greater distance. Similarly, for the slower part, I'll be getting the secondary wave nearer to the sphere. So if I join all the tangents, see there will be various secondary wavelets. So when you'll be joining, you will be getting a continuous curve. So this continuous curve that we'll be getting is the refracted ray or the incident ray?
Refractor.
Refracted ray. Now see, just the case opposite to a convex mirror is the concave mirror. So convex lenses are converging lens, convex mirrors are diverging mirrors, and concave mirrors, these are the converging mirrors. Whereas in case of concave lens, we have seen that they are diverging lens. So see, in case of a concave mirror is also a part of a sphere which is polished or silvered on the outer side. So all the reflection phenomena occurs on the inner side only. Like if this is the incident wave and all the reflection has to occur, then what will happen? This is a general case. I have not considering it for the wave phenomena. So since it is a converging mirror, it will converge it on its focus or wherever on its principal axis. So again, some part of light will be going, and this is a general case for a concave mirror. Now see, let us relate it to the wave theory. Convex mirror wavefront. Okay, Noor, I'll explain both of them. Convex mirror and concave mirror once again. Just a second, let me complete it for the concave mirror. Now see, for the concave mirror, this is the silvered portion. This is the glass portion, I mean. These are all the glass portions. So again, according to the speed of light and all the phenomena, since it is coming nearer, this will be further away. For this, it is away. This is far away from itself. So what will happen? This will be nearer to itself. And similarly, this will be similar to the upper portion. So this will be like this. So if I'll join all of them, I'll be getting somewhat spherical. So this, I'll draw it again. These are. So finally, what is this red line representing? This is the refracted wavefront, and this ABC is the incident wavefront. Now see, I am repeating for convex mirror and concave mirror again. All right, so listen it carefully for concave mirror and convex mirror. Now see, for the concave mirror first, the central part B of the incident wavefront has to travel the greatest distance? Yes or no? The central part of B has to travel a greatest distance before getting reflected compared to the margins A and C. So therefore, the central portion B of the reflected wavefront, this is closer to the mirror than the marginal portions D. Noor, understand this. This central part, this B, that's why I have drawn A, B, C. A and C represent the margins of the incident wavefront, and B represents the middle portion of the wavefront, the central part. So the central part of incident wavefront, this B, this has to travel a greater distance before getting reflected. Yes or no? This is a greater distance compared to the margins. Yes?
Yes, ma'am.
Yes.
Now see, therefore the central portion of this secondary wavelet, this is closer to the mirror than these marginal portions, because over here the distance is larger, over here the distance is lesser. So the case is just similar to the lens only, it's just that we have considered mirror now. So the reflected wavefront is spherical and it converges to the focus. In case of convex mirror, the central part B, this has to cover a lesser distance than the margin. So A and C, these have to cover a greater distance. Since they have to cover a greater distance, these wavefronts are closer to the mirror. That's why when you will join, you will be getting a spherical wavefront. Is this clear now? All the behavior of the wavefronts for various devices.
Yes, ma'am.
Reflected. M is reflected because in case of mirror. For mirror, it will be reflected. For mirror, it will be
Teacher, you
reflected.
have written refracted.
Did I say refracted?
Yes, teacher.
Okay,
Teacher, you
sorry.
have written that.
No, wavefront will be refracted. Okay, you're asking me this will be refracted. This,
Yes, teacher,
these,
clear.
okay. That's, I was just comparing it to them only, these, in order to understand, because we have written it for refracted wavefront. Actually, it will be reflected wavefront only. That's why I was saying reflection, because in case of mirror, these will be reflected wavefront only. I have actually compared it to the previous. So you are able to understand. I'll write it reflected. Just to compare it to the previous case. That these are only what we have been discussing. So these will be reflected now. Reflection is occurring. In case of mirror, refraction are not occurring. So this will be a reflected wavefront only. This will also be a reflected wavefront only. It's just that the way we have got them, the refracted wavefront, we are getting these ones. Any other doubts in this behavior of all the devices with regard to a plane wavefront?
No, ma'am.
Okay, so just note it down, and wherever you get stuck, ask me. I'll repeat it.
Yes, teacher, done. Yes, teacher, done.
Completed?
Yes, teacher.
Oh. See, let us prove the laws of reflection on the basis of wave theory. So the first law of reflection was that angle of incidence is equal to angle of reflection. So see, first we are talking about reflection, then we will be considering refraction. Now, just in order to understand, I have taken a plane surface, plane reflecting surface, let's say XY. This is a plane reflecting surface. You can consider it as a mirror also, a plane mirror. Now see, a plane wavefront, let's name it something as AB. This is incident on this plane reflecting surface. Let's say this is AB. So a plane wavefront AB is incident on the plane reflecting surface XY. So both the wavefront and the reflecting surface being perpendicular to the plane. Now let's see. First, what happens? The wavefront touches the reflecting surface at V, and then successive points. Let's name it as C, point CS. We have point C, we have point A, we have point B over this side. Now see, if since this is tilted, and if I draw the spheres again, the spherical curves for the secondary wavelengths. So see, in case of A, I'll be getting a curve all over this side like this. This is for A. And for B, I'll be getting a curve over this side. So a curve will be over here and another curve will be over here. One for A and one for B. Now see, if I join these, if I join these two, let's name it something CD. If I join these, so in according to Huygens principle, all the points, this is C, this is the same point. I erase the previous one. Now see CD. I have received the CD. So CD is the reflected wavefront because of the reflection from this plane mirror. Consider this as a plane mirror only. AB is what? AB is incident wavefront. AB is the incident wavefront and CD is the reflected. CD is the reflected wavefront. Now see, first the wavefront touches the reflecting surface at C and then at the successive points towards C, like these. All the points will be having their own and generating their secondary wavelength. Now see, what will happen if I draw, let me take another color. If I take the rays of light perpendicular to the incident wavefront, just perpendicular. So one of them will be like this and the other one that is perpendicular to it. This will be somewhat like this. Okay, these are just incident rays. These are the incident rays. And since I've told you, rays are always perpendicular to the wavefront. So this is making an angle of 90 degrees. This is also making an angle of 90 degrees. Now see, according to the properties of plane mirror, if a light ray is incident, and let me draw a normal as well. What should happen? If a ray of light is incident, what should happen next? Should it get refracted? Should it be transmitted? what should happen? Yes,
Reflected.
reflected. Yes, reflection will occur. General phenomena of reflection will occur. So what will happen? This will get reflected towards some this part. And similarly for the incident ray, this incident ray, this will also be getting reflected. So these white lines, these are the reflected rays. See, this yellow part was the incident wavefront. This created a reflected wave. And since rays are always perpendicular to the wavefront, we have an incident wavefront, and we have two incident wavefronts, basically random. Since these rays are incident on the plane surface, according to the properties of plane mirror, it will reflect it with the same angle. So it has reflected. So these white lines represent the reflected rays. Now what you have to understand is that the distance, that is this distance from this point C to A point, or from B to this point D point, this is actually, this distance can be calculated using V multiplied by T. That is how we calculate the distance. Whatever is the speed multiplied by the time can give us this distance, and whatever is the speed for this will also give us the distance. So V into T will be for this sphere. So are these terms clear? Incident wavefront, reflected rays, and the incident ray.
Yes, ma'am, it's clear.
Okay, and see, VT will be CT only, means speed of light multiplied by time. So during the time disturbance from A, this reaches the point C, secondary wavelets from B have spread over hemisphere, and we have got reflected wavefront, and because of the incident rays we have reflected rays. Now see how to prove the reflections law. Let us consider this angle BAC. See, this point is not A because lines have point A is only here where it is intersecting. So take this angle BAC. If I take the angle AC is equal to what? You are asking, Noor? AC equals to BD.
Yes, ma'am.
Yes, these are equal. Actually, drawing on this makes them unclear. So that's why these are equal. And this is making an angle of 90 degree only. These are equal. These two lines are equal. So see, angle this BAC. If I take this angle BAC, this angle BAC is equal to this angle. This is also making an angle of 90 degree. So this angle BAC is equal to angle CDB. Okay, before that, angle of incidence for the wavefront is this. This is the angle of incidence for the wavefront. For the incident rate is this, but for the wavefront, see, things get reversed for wavefront. This is angle of incidence. You consider the angle from the rays, from the wavefronts, and with the refracting surface. That's why this is the angle of incidence. Similarly, for the reflected wavefront, this will be the angle of reflection of the wavefront. So this is the angle of reflection, and this is the angle of incidence. So see, BAC will be equal to CDB. Apart from this, we are considering these two triangles. In triangles ABC and triangle BDC. So these two angles are equal. BC is the common side for both. And as I've told you, these two lines are equal. AC is equal to BD. AC is equal to BD. So if you remember from your previous classes, one angle is equal to, both of these angles are equal to 90 degrees. One side is common. These sides are common because both of them have speed CT or VT. Both of them have speed VT. So from SAS property of congruency, if you recall from your lower classes, are these two triangles similar to each other? Can I say triangle ABC is similar to triangle BDC
Yes, teacher.
Yes, ma'am.
according to congruency, SAS property? So if two triangles are congruent to each other, all the properties are similar for both of them. So this means this angle will also be equal to this angle. So what is this angle? This is angle of incidence. This is equal to angle of reflection. So this proves the first law of reflection. Clear?
Yes,
Yes, ma'am.
teacher.
No. So just write this as well, then we'll do it for refraction. Let me know when you all are done. Okay, so let us discuss it for refraction. This was for reflection. Now
Teacher, not
see,
that.
just the thing that will differ in case of yes, yes,
Teacher,
somebody.
not.
You have not written.
No, teacher, I was right.
Okay, okay. Fine.
Yes, teacher.
All right. So let's see in for refraction. So the difference that will come is that the reflected ray, instead of getting the reflected ray, we'll be getting a refracted ray. So I think this will be easier than the reflection case, since the refraction you have studied in detail. Now see, let's say this is an incident wavefront. This is an incident wave. So again, this point, let's name it as B, let's name this point as A. Now see for A and B, if I draw the secondary wavelets, so instead of getting them over this side, now I'll be getting them over this. Why? Because this is a refracting surface. This is a refracting surface. Previously, that was a plane mirror, which was a reflecting surface. So now this is a refracting surface that I have. So let's say for A, I have this secondary wavelet, and for B, I have this. Since this is closer to it, sorry, this is far away from it, and this is closer to it, I'll be getting somewhat this kind. Now let me connect them. If I draw a tangent, it will be like so. For B, it must be like this, and for A, it will be like this. So what is this? What is this red line?
Refractive wavefront.
Exactly, this is a refracted wave. Previously, that was the reflected wavefront. Now we are getting the refracted wave. Ahmed, your mic is on. Ahmed. Okay. Now, since this will also be perpendicular to the incident wavefront, so we have an incident ray of light. Again, we'll be having a normal. Normal will be there. Now see, will I be getting, if this is the incident ray of light, this blue line is the incident ray, not the wavefront. This is general incident ray of light that you have studied. And this is the refracting surface. So this light should go down. It means it should bend. It should refract instead of getting reflected. So now see what will happen. If this is the incident wavefront, this will bend. And if I say this is a rarer medium, and if I say this is the denser medium, and light is going from the rarer medium to denser medium, so light rays should bend towards the normal or away from the normal?
Towards the normal.
Towards normal. So this is now, this white line is representing now the refracted ray, not the refracted wavefront. This is the refracted ray of light. Similarly, let us just take another end for another end also. Let's say for this. This is perpendicular to B again. This is also another wavefront, another wave of light. So see, another normal will be drawn for this. And this will also get refracted. Similar to this will also get refracted. Now see, again, similar to the previous case, the speed will be, let's say, V1 into 2. We are not aware of the speed now, and speed will be different now. Speed of light in medium 1 is V1. V1 is the speed of light in this. This is the first medium. In medium 1, whereas this is the medium 2. So let's say V2 is the speed of light in medium 2. And see, let us consider the refractive index also. If N1 is the refractive index for this medium, and N2 is the refractive index for the second medium. So if this medium is rarer, first medium is rarer, and second medium is a denser medium, then obviously V1 is greater than V2. speed of light is more in the rarer medium than the speed of light in the denser medium. Now let's see few calculation parts. If I take this triangle, ABC, let's name this some C. If I take this triangle ABC, in triangle ABC. Okay, before this, one more thing. The incident angle for the wavefront will be this, and the refracted wavefront angle will be this. R will be this now. Previously, it was above the axis, above the reflecting surface. Here, it would be this, below it. So now let's see, and this will be perpendicular definitely. This will be perpendicular. So see, if I take the sine of this angle, sine I. So in this triangle, yes, tell me, looking at the figure, sine I should be equal to what? This is the perpendicular, this is the angle. Sine I should be equal to what in terms
BC
of
by
AC?
AC.
BC by AC. Sine I would be equal to BC by AC. Now for the other right angle triangle, let's name this point as D point. Let's name it as D point. So in triangle ADC, we have to take sine R. Means this triangle ADC, we have to take sine R. So this is again making an angle of 90 degrees. So what should sine R be now? This is the angle, this is 90 degrees.
AD by AC.
AD by
AC.
AC, exactly. AD by AC. So sine R would be AD by AC. So if I take the ratio sine I divided by sine R, this will be equal to, see, AC is common for both of them. This will be BC by AC, and since sine R is getting divided, this will be the reciprocal of it. So it would be AC by AD. AC will get cancelled. Now see, what is BC, sorry. BC is this, and this is V1 into T. BC is the incident light, so that is V1 into T. Similarly, for AD, this is V2 multiplied by T. Time will get cancelled, we'll be left with V1 by V2. So sine I by sine R, if this is equal to V1 by V2, this gives us the ratio of V1 by V2 is basically what? The refracting index. If you can write it as N21 for medium 2 with respect to medium 1. So which law is this? Any law are you able to recall?
Snell's law.
Snell's law, exactly. So this proves your Snell's law. So using reflection, you were able to prove angle of incidence is equal to angle of reflection, and using refraction on the basis of Huygens theory, you are able to prove Snell's law of refraction. So the constant that you are getting is the refractive index for the second medium with respect to the first. So just note this down as well. Written?
Yes, teacher.
Okay. So any doubts from this? Huygens principle, wavefront, spherical wavefront, plane wavefront, cylindrical wavefront, refraction, reflection. Any queries? If it's clear, then let us begin with diffraction. See, let us understand what is meant by diffraction. If I take a slit, this is a slit. See, just to represent you, I have drawn it very broad and thick. It's actually a very, very narrow slit. So this is a slit. Now see what will happen. I have passed some light, and this is my screen. This is the final screen. This is the screen. Now see, if rays of light are coming from all the directions, then what should happen? The rays of light should fall over this. Rays of light should reach over here. But since this is an opaque object, this is an opaque substance, then the light should get blocked from it. This should be blocked. So accordingly, what should we get? We should get a shadow on this portion where light is not reaching. Yes or no? There should be dark opaque shadow over this side, which is equal to the length of this. Yes or no?
Yes, ma'am.
Yes, ma'am.
But see what actually happens. Only this part should have the dark colored region, that is the shadow. But in actuality, if you will observe this, what will happen? Some rays that are crossing this will bend and reach them. According to our knowledge that light travels in a straight line, this should have been the case. But what are we observing? Instead of getting the whole shadow, we are getting shadow only in some part. Let's say this part only. We are getting the opaque part, and rest of the part of the screen is receiving the light. So this aperture is very small. This is very, very small as compared to the wave. So light travels in a straight line. However, whenever light passes through a small hole or a very small diameter, then there is a certain amount of spreading of light. Similarly, when light passes an obstacle, it appears to bend round the edges of the obstacle and enters the geometrical shadow. So this phenomena of bending of light around the corners of small obstacles or apertures, and then its consequent spreading into the regions of geometrical shadow, this is what is known as the phenomena of diffraction. Like if you take a narrow aperture like this, and there's a source of light, then what will happen? Because this is a very narrow aperture, the light rays will get bent from the corners of it, and the geometrical shadow will be here only. And if you take a very, very small obstacle like this and a source of light, what will happen? From this source of light, this part we'll be getting the geometrical shadow. So this is just an example. Basically, this phenomena, this bending of light that is occurring, this is what is known as diffraction. And the shadow is not very sharp that we are getting. This shadow is not sharp. This shadow is not sharp because the light rays are able to reach it. So this phenomena that light bends around the edges, this is known as the phenomena of diffraction. Understood?
Yes, ma'am.
Okay. Now see, diffraction is also of not a single type. Diffraction are also of two major types. We have two major types of diffraction. First one is the Fresnel's diffraction. Second one is the Fraunhofer's diffraction. Let us understand what is meant by Fresnel diffraction and Fraunhofer's diffraction. See, in case of Fresnel's diffraction, the source and the screen are placed very close to each other, are placed close to the aperture or the obstacle, and the light after diffraction appears converging. The light after this traveling through this appears converging towards the screen, and hence no lens is required to observe it. So the wavefronts, basically, the incident wavefronts over here are the spherical or the cylindrical wavefront. Spherical or the cylindrical wave. Whereas in case of Fraunhofer's diffraction, the source and screen are placed at a larger distances, effectively at infinity from the aperture or the obstacle, and converging lens is used to observe the diffraction pattern. So since the rays or the source is placed effectively at infinity, the wavefront that we should get should be the plane wavefront. So the wavefront that we'll be getting is the plane wavefront. Now see, let us understand what is diffraction phenomena, how it occurs through a single slit. Means if there is a one single slit over. So see what will happen. Let me take a lens. I have taken a lens L1. Let's say this is the lens L1. So a source of monochromatic light is placed at the focus of the convex lens L1. So what will happen? What is the tendency of a convex lens? To converge or diverge?
Converge.
Converge. Converge. Yes. So what will happen? So a parallel beam, if I place the source of light on the focus, then what should be the nature of the refracting rays? When the object is kept at focus, what happens?
It will become parallel.
Parallel, exactly. A parallel beam of light will be observed. If this is kept, a parallel beam of light rays will be observed. This will be parallel. So since parallel rays are there, then the kind of wavefront that we'll be getting is the plane wavefront. So this is the wavefront. I'm naming it as WW, means this is the wave. So this gets incident on a narrow rectangular slit. Let's say this is the narrow rectangular slit. So the length of this, the width of this is A. Width of the slit is A. So this is a single slit. This is the single. Now see, the incident wavefront disturbs all part of the slit. If I say AB is the slit, what happens? The incident wavefront disturbs all parts of the slit AB simultaneously. Now we have discussed Huygens principle, Huygens theory in detail. So according to Huygens theory, all the parts of the slit AB will become source of secondary wavelets, which all start in the same phase. Yes or no? Secondary wavelets, this phenomena was given by Huygens theory. So these wavelets spread out in all directions, which is actually causing diffraction. So if I take the rays, these rays will be somewhat like this in different directions, spreading out. Let's say one is this, other one is this. It will also be going in downwards direction as well, but I'm not drawing it in the downwards direction. Just assume it that it is going in the downwards as well, because it will be a messy diagram then. You will not be able to understand what is it. Two, I think, upward, and the front one is better. See, so these will be the different. Yes.
These red lines are secondary wavefronts.
What?
These red lines are secondary wavefronts.
Yes, yes. These are the secondary wavefronts. These, see this source AB. The parts of all the parts of the slit AB will become the source of secondary wavefronts, wavelets. So which all start in the same phase. So these wavelets spread out in all directions. These are just these wavelets. These are the secondary wavelets only. These are spreading in all different directions. So this is causing the diffraction of light. Now see, just in order to obtain it on screen, because these are various lights, what we can do, we can take, in order to converge it, what kind of lens should I take?
Convex lens.
Convex.
Convex lens. So if I place a convex lens of larger aperture, if I have taken, and this is the screen, this is the final screen. Now see what will happen. According to the property of the convex lens, these will converge it at a particular point. Similarly, for the wavefronts that were in the passing through the middle. These. So see, this will be the direction because of the convection. This is the screen where we are obtaining. This is the lens, second lens. L2, a second lens has been placed. So see, these wavelets spread out in all directions, causing diffraction of light after it emerges through slit AB. So suppose the diffraction pattern is focused by this convex lens L2 on a screen in the focal plane, just in order to obtain the rays, because these are spreading in all directions. And one more thing, can anyone tell me whether it is Fresnel's diffraction or Fraunhofer's diffraction?
Fresnel's diffraction,
Why Fresnel's diffraction?
because the distance between the source screen is finite.
Is finite.
Yes, teacher,
See,
finite.
see, we have drawn it very closely just because we cannot draw infinite. How is it infinite and how is it finite? You have to identify through the nature of the wavefront. When do we get the plane wavefront? Plane wavefront is for Fraunhofer's or Fresnel's?
Fraunhofer's.
Fraunhofer. So this is for a Fraunhofer's only. You can identify it easily using the nature of the wavefront. So this will be a Fraunhofer's diffraction. So see, let's say this is θ1, this is some θ2, these are the various angles. And AB, A is the width of the slit. Now see, one term that you have to be aware is the path difference. If this is closer to the, because of the margin, this is closer and this is far away. So this extra part that you are getting, that is basically the path difference. Understood? Can you see this extra stretch? If let me draw a perpendicular. If I draw a perpendicular to it, let's name it something. This is D, this is N. DN. Are you able to see this extra stretch? DN.
Yes, ma'am.
This is the path difference between the wave reaching this point P. Let's say, oh, I haven't drawn this. Nobody has even pointed out. These rays I have drawn parallel. These will also get converged because of the lens. Because of the property of convex lens, these lines will also converge. Now see, they will converge at a point. Let's say this point is O. So this part that you are getting in the middle, all the secondary wavelets going straight across the slit AB, these are focused at the central point of the screen. So this central point, this is known as the central maximum. This is known as the central maximum. Now see, we were calculating the path difference. In order to understand the path difference, we just require this. Let us make it as a triangle only. So we need dn. This dn is the path difference. So for the calculation of the path difference between the waves reaching the point P from these points. So let's see, if in this triangle, if you take in triangle ADN, this triangle, if you take, if this is the angle, this is my triangle, this is the angle, this is a perpendicular drop, so this will be 90 degree. What should be sine theta? Yes, what should be sine theta?
dn by da
dn
by da.
by dA, exactly. It should be dn by AD. This dn by AD. So see, dn is the path difference that we are searching for. So this is equal to AD, this AD multiplied by sine theta. What is AD? This is the width of the slit. So dn is equal to A sine theta. Is it clear? This is the path difference. Is the path difference clear?
Yes, ma'am.
Okay, so just write it down first.
dn is path difference.
Yes, path difference. See, this is the first part for A point. This is the path for the B point. How do we take the difference? The extra stretch that we are getting of the path. This is the extra. If you subtract this from this, you will be left with this only. So this is the difference of the path. Okay.
Yes, teacher.
From this page, just write the definition of diffraction. You don't need to draw this. These were just for your explanation. Then write the types of diffraction. After this, Abdullah, just a small 2 points are left. Conditions for maximum and minimum. Just 2 small topics are left. Then the class will be over. Yes, no. The central has bright light. It's the central bright thing because they are adding constructively to produce this point. See, for the position of minima, for the next secondary minima, we should have a general equation for the condition of, let's say, some nth minima. So condition for nth secondary minima. See, the path difference is actually the wavelength. If lambda is the wavelength, then path difference should be equal to lambda. But see, if we have various types of fringes, first, second, third, till nth, so for each path difference, it would get multiplied. So this will be equal to n lambda. And we have also calculated path difference equal to a sine theta. So for some nth theta, this will be equal to a sine theta n. This is equal to n lambda. Now see n over here, n is equal to 1, 2, 3, up to so on, because various kinds of minima can be obtained. So 1, 2, 3, it can be any. And if you have to calculate sine theta for the nth, say let's say some nth secondary minimum, it would be n lambda divided by a. And if you use small angle approximation, according to small angle approximation, sine theta is almost equal to theta. So theta will be equal to n lambda by a. So this is for the angular, if you wish to calculate for the nth second maximum, minima. Now see, if you take the linear separation, means in case of y, that is the separation between these, all these. If you take it as for y, for first, for second, for all the maxima that you are getting. So in case of, if you take it for the y, the linear separation, this will be equal to angle multiplied by the distance. That's how we take it for an arc. R is equal to, the length is equal to r theta. From there, you can say yn is equal to theta d. Now see, theta n, if you wish, you can substitute the value. So yn will be equal to n lambda a, this part, and then theta. So yn will be n lambda d by a. So you have to use this when? You have to use this when only small approximation is valid. If small approximation is not valid, then you are not allowed to use this formula. If small approximation is not valid, then you use tan theta equals to yn divided by d. This is for the case when small approximation, angle approximation is not valid. See, yn is this. Yn is this. This separation, this is yn. And what were you asking, Noor? D is this separation from the screen and the slit. This is d, this is yn. So if it is substituting and this is making an angle, subtending an angle in the middle, that is d, that is capital D, and that is capital Y. So angular separation is theta. All right, angular separation, we have taken it as theta. So when you can use tan theta for small approximation or not?
Not for small approximation.
Small angle approximation, you have this. See, when the small approximation angle is not valid, then you have to use theta. Now see, this was the case for minima. Now see, if similarly I have the case of condition of nth secondary maxima. Now see, condition for secondary nth maxima, just the change occurs in the path difference. Now the path difference that you will be getting is 2n plus 1 lambda by 2. You have to remember this. And n is again equal to 1, 2, 3 and so on. Now see, the previous steps will be same, and a sine theta will equal to 2n plus 1 lambda by 2. So if you wish to calculate sine theta for the nth secondary maxima, this would be 2n plus 1 lambda a divided by 2. And again, if you use small approximation, similarly, for the small approximation, means small angle approximation, if your angle is very small, sine theta will almost be equal to theta n. This will be equal to 2n plus 1 by lambda by 2a. And again, y will be equal to, for the linear separation, this will be equal to, by n will be equal to 2n plus 1 lambda by 2a multiplied by 2. So it would be just the similar for the minima. Just note it down for the minima and maxima.
Done, ma'am.
Done?
Yes, ma'am, done.
Yes,
All
yes.
of you?